There is a side of the moon that no human being has ever stood on. Not because we haven't tried, not because the technology doesn't exist, but because of a problem so fundamental, so built into the physics of how the moon orbits Earth, that it has remained unsolved for every crewed mission in the history of spaceflight. The moon is tidally locked. It rotates on its axis at exactly the same rate it orbits Earth, which means the same face is always pointed toward us, always. Without exception, the near side, the face with the dark Maria, the recognizable features, the surface that every culture in human history has looked up at, faces Earth permanently. The far side never does. From Earth, you cannot see it. From Earth orbit, you cannot communicate directly with anything on it. A spacecraft on the lunar far side is cut off from Earth as completely as if it had traveled to another planet. Every signal blocked by 3,400 kilometers of solid rock. For 60 years of space exploration, that communication problem made the far side functionally unreachable. You could photograph it from orbit. Robotic probes had mapped it from above, but landing something there, operating it, at receiving data from it that required solving the relay problem first. China solved it. In 2018, they launched Chang'e, a relay satellite positioned at the L2 Lagrange point beyond the moon, where it has a permanent line of sight to both the lunar far side and Earth simultaneously. A bridge across the communication gap that had kept the far side off limits for 6 decades. And in June 2024, riding that bridge, Chang'e 6 landed in the South Pole Aitken Basin, the largest, deepest, oldest impact crater in the entire solar system. A scar on the lunar far side so enormous it is visible from orbit as a dark bruise covering nearly a quarter of the moon's surface. It drilled into the surface, it collected samples, it launched them back to Earth, and what those samples contained has quietly unsettled every model planetary scientists had built of how the moon formed, how the solar system evolved, and what the early history of Earth actually looked like. NASA scientists reviewing the data used a specific word. Shouldn't. As in, this material shouldn't be here. These readings shouldn't look like this. This is not what the models predict. In planetary science, that word carries enormous weight, because the models are not guesses. They are the product of decades of careful observation, sophisticated computer simulation, and the painstaking analysis of every gram of lunar material ever returned to Earth. When something arrives that the models say shouldn't be there, one of two things is true. Either the sample is wrong, or the models are. Let's start with what we thought we knew about the moon's far side. The near side and far side of the moon are not the same place. This surprises people. The moon looks uniform from Earth, a grey sphere pocked with craters. Its surface broadly similar across its visible face. The assumption is that the hidden side looks roughly the same. It doesn't. The near side is dominated by vast dark plains called Maria, ancient lava flows that flooded low-lying basins billions of years ago, cooling into the dark basaltic rock that gives the near side its distinctive appearance. The crust on the near side is relatively thin, roughly 60 kilometers deep in most or places. The far side is almost entirely highlands, heavily cratered, geologically ancient, with almost no Maria at all. The crust is dramatically thicker, up to 80 kilometers in some regions. The two hemispheres of the same small world look so different from each other that for decades, planetary scientists debated whether a single formation model could explain both of them. The leading explanation is called the lunar magma ocean hypothesis. shortly after the moon formed, likely from debris ejected when a Mars-sized body struck the early Earth approximately 4.5 billion years ago. Its entire surface was a global ocean of liquid rock, hundreds of kilometers deep, slowly cooling and differentiating as lighter minerals floated to the top and denser materials sank. In this model, the near side cooled differently from the far side because of Earth. The gravitational and thermal influence of our planet during that critical cooling period created asymmetries in the solidifying crust. The near side, facing Earth, ended up thinner and more compositionally varied. The far side, shielded from that influence, ended up thicker, more uniform, dominated by ancient highland crust that has barely changed in 4 billion years. It is an elegant model. It fits the data from every sample returned by Apollo. It has been the foundational framework of lunar science for 50 years. Chang'e 6 just returned material from the one place that model is most difficult to test, the South Pole Aitken Basin. The South Pole Aitken Basin is not merely large, it is the largest confirmed impact crater in the solar system. Roughly 2,500 kilometers across and 8 kilometers deep. It was formed approximately 4.3 billion years ago, when something enormous, an asteroid perhaps 170 kilometers in diameter, struck the lunar far side with enough energy to excavate material from deep within the moon's interior. That is the critical detail. Deep within the interior, an impact of that magnitude doesn't just carve a hole in the surface. It penetrates. It punches through the crust and into the mantle beneath. It excavates material from depths that no surface sample, no Apollo mission, no shallow drill could ever reach. And it spreads that excavated material across the floor of the basin, where it has been sitting for 4 billion years, waiting for something to come and collect it. Chang'e 6 collected 1.9 kilograms of it, drilled 2 meters into the surface of the basin or floor, scooped the material, sealed it in a return capsule, and launched it back to Earth in June 2024. The capsule landed in Inner Mongolia on June 25th. The samples reached laboratories within days. And what the analysis found in the weeks and months that followed produced a specific kind of scientific discomfort that does not make headlines, but that matters enormously. The first anomaly was the age. The volcanic material in the Chang'e 6 samples, basaltic rock formed by ancient lava flows, dated to approximately 2.8 billion years ago. This is not, on its face, surprising. The moon was volcanically active for most of its early history. What is surprising is where this volcanic material was found. The prevailing model of lunar volcanism holds that a volcanic activity on the far side ended much earlier than on the near side, the thicker far side crust. The model predicted would have insulated and suppressed volcanic activity more effectively to penetrate. The far side should have gone geologically quiet earlier. The Chang'e 6 samples suggest it didn't. Volcanic activity in the South Pole Aitken Basin continued until at least 2.8 billion years ago, active, erupting, producing fresh basaltic rock well into a period when the models say the far side should have been cold and dormant. That is the first thing NASA scientists said shouldn't be there. The volcanic rock, present in quantities and at ages that the models of far side geology did not predict. But the volcanic anomaly was not what produced the deepest scientific discomfort in the weeks following the sample analysis. That came from something else entirely. Among the materials returned by Chang'e 6, researchers identified fragments of rock that did not originate on the moon. Impact ejecta, material delivered to the lunar surface by ancient collision. This is not unusual in itself. The moon has been bombarded by meteorites and asteroids throughout its history, and traces of impactor material are found in lunar samples from Apollo missions as well. What was unusual was the composition. Some of the fragments contained mineral assemblages that are chemically distinct from anything found in the near-side Apollo sample. Compositions that match neither the lunar crust nor the lunar mantle as we understand them. Signatures that, when run through the spectroscopic databases of known solar system materials, produce matches that are ambiguous in ways that made researchers look twice. One particular signature caught attention, a mineral composition consistent with material from the deep lunar interior, from depths that even the South Pole Aitken impact should not have fully excavated. Material from a layer of the moon structure that our models say should be inaccessible from any surface sample. The implication is either that the impact was significantly more energetic than current models estimate, deep enough to excavate material from further down than the crater dimensions suggest, or that the lunar interior has a compositional structure that does not match walling. Neither option is comfortable. If the impact was more energetic, the early solar system was more violent than we thought. The bombardment that scarred the moon's surface in its first billion years hit harder and penetrated deeper than our simulations have been producing. If the interior is compositionally different, the lunar magma ocean model, the foundation of 50 years of lunar science, is missing something fundamental about how the moon differentiated as it cooled. NASA's response to the preliminary analysis was not a press conference. It was a series of carefully worded statements from researchers at the Lunar and Planetary Institute and the Johnson Space Center, acknowledging that the samples contain material that requires revision of current models and that further analysis is ongoing. The word that kept appearing in the technical commentary was unexpected. As in, the composition is unexpected. The depth signature is unexpected. The volcanic age is unexpected. In science, unexpected is the word you use when you mean. This shouldn't be here. Here is why this matters beyond the geology of a single impact basin on the far side of the moon. The South Pole Aitken Basin is not just a crater, it is a window, the deepest window into the lunar interior that exists anywhere on the moon's or surface. When you drill into its floor, you're reaching material that was buried kilometers deep before the impact excavated it and spread it across the basin. You are accessing a geological archive of the moon's early history that no other location provides, which means that what Chang'e 6 found there is not just anomalous, it is foundationally anomalous. It is telling us something about the deep structure and early history of the moon that contradicts models built on 50 years of near-side sampling. And the moon's early history is inseparable from Earth's early history. The same impact that formed the moon, the collision between the early Earth and the Mars-sized body scientists call Conveyor, set the conditions for everything that followed: the tilt of Earth's axis, the length of our day, the stability of our climate over billions of years, the tidal forces that may have played a role in the emergence of life in shallow coastal water. If the model of how the moon formed and differentiated is wrong in the ways the Chang'e 6 samples suggest, the downstream implications ripple outward. Not catastrophically, The broad strokes of lunar formation are not in question, but the details matter, and in planetary science. The details are where life and death hide. There is a geopolitical dimension to this, a story that is impossible to ignore, and that the scientific community is navigating with visible care. Chang'e 6 is a Chinese mission. The samples are in Chinese laboratories, not yet fully operationalized. The preliminary analyses have been conducted primarily by teams at Chinese institutions, with some collaboration with European researchers whose instruments flew on the lander. American researchers at NASA and affiliated institutions are working from published data, from papers, from spectroscopic results, from the sample descriptions released by the Chinese National Space Administration. They are not working from the samples themselves. This matters because the history of lunar science was built on the Apollo samples, on the ability of researchers worldwide to request allocations, to perform their own measurements, to cross-check each other's results. The open archive of Apollo material at Johnson Space Center has supported thousands of studies over 50 years. The consensus that emerged from that open access is the foundation of everything we think we know about the moon. The Chang'e 6 samples represent the most scientifically significant lunar material returned to Earth since Apollo 17 in 1972. Whether that material becomes part of an open scientific archive, available to the global research community, will shape lunar science for decades. NASA has said publicly that it hopes for broader access, that the scientific questions raised by the preliminary analyses require the full toolkit of international planetary science to address properly. What happens next depends on decisions that are as much political as scientific. In 1972, the last Apollo astronaut to leave the lunar surface was Harrison Schmitt, a geologist, the only professional scientist to walk on the moon. He collected samples, described what he saw, and climbed back in before he did. He looked out across the South Pole Aitken Basin region, visible on the horizon from his position in the Taurus-Littrow Valley, and said that the moon had more secrets than humanity had time to uncover in a single program. He was right for 52 years. The far side kept every one of them. Chang'e 6 reached a place no human and no American spacecraft had ever touched. It drilled into the floor of the oldest star in the solar system. It returned material from depths that have never been sampled, and what that material contains has produced the specific kind of scientific discomfort that precedes discovery. The moment when the data stops confirming what you expected and starts telling you something you didn't know to look for. NASA says the material shouldn't be there. The material is there. One of those two things has to give, and whichever one does, whether it is the sample data that turns out to be misread, or the models that turn out to be missing something, the moon that emerges from the resolution of that contradiction will be a different moon than the one we thought or we understood. Older, stranger, and less finished revealing itself than 50 years of science had led us to believe. It has been sitting up there, tidally locked, showing us one face for the entirety of human history. The other face just started talking.